have Jude Maul and then Dave Huggins, who will be covering the long-term agricultural research site network that's organized by the USDA Agricultural Research Service. So I'll turn it over to Jude. Thanks so much for being with us, and please take it away.
I'm Jude Maul, and I'm with the USDA ARS in Beltsville, Maryland, and I'm a research ecologist there in the Sustainable Ag Systems Laboratory. And today I'm going to give you, you folks, a high-level overview of the USDA Long-Term Agricultural Research Network. And then Dave is going to dive into a little more of our activities in the soil realm. So this research network grew out of some of the challenges facing agriculture in the 21st century, specifically some topics that were tackled by the USDA in the sort of late 2000s, which centered around sustainable intensification, growing more with less, preparing to feed 9 billion people by 2050. And some of the terms that were sort of thrown around were 20% more quality products, 20% reduction in environmental resource impacts by 2025. And you could tell that's kind of like a lot of political terms. And so those were outlined as some of the goals for us to challenge ourselves with over the next few years from the standpoint of the Agricultural Research Service. And really, those types of goals really have to be put into the context of human health and quality of life. And those are outlined in some of these papers here, where those goals of understanding and of managing the growing world population really had to be balanced with how that would impact the quality of life for all people in the world. 25% of the Earth's lands are already degraded, and there's potential for sustainable intensification to affect lands that are particularly vulnerable. This can result in things like emerging pathogens and is complicated by ongoing climate change. So this threatens food security, and this really takes more than a reductionist perspective to solve. And that garnered a number of calls for action. And these papers here outline some of the early discussion talking about national scale agricultural research goals, and talking about how looking at agriculture from a holistic national standpoint can help us understand some of the larger environmental problems facing us and the impact of these intensification and climate change. The ecological NSF and the ecological sort of domains had already taken a national approach at looking at how ecotones and varying ecological sites were responding to both human impact and climate change. And that was already taking place within the USDA as well, specifically focusing on watershed scale networks. And these sites were set up around the country within agricultural production regions, and was really sort of the predecessor of a national scale network for agricultural research. In 2012, there were a number of meetings taking place in around the country, really, bring these ideas to light and talking about how coordinating research at a national scale gives us inference domain to a much wider degree than focusing on specific production systems in specific locations, where there's value in both the connectivity of those at the landscape and regional scale may help us understand how the intersection of land use management and policy impact each other. And going forward, a number of strategies were proposed to develop this type of network, and really based on this foundation in science. And ARS is really the research agency, and we don't do policy. And so our goal was to set this network up as a research base, sort of a research drawing a blank on the word, but laboratory, so to speak, on the landscape, based in a foundation of science. And our goal really here is to make sure that the data that is used to develop policy is very robust and is based in a real understanding of the systems. And I'm not going to go through this whole network of research strategy, but really it's a systems approach to using information in an iterative fashion with input from stakeholders to really understand what is happening in our systems and how our actions at the landscape level are having impact. So in the early 2012 or so, a number of sites were identified. Here are those sites overlaid upon the NEON domains that were originally identified through the NSF NEON program, which are ecological domains. And many of the ARS sites match some of the sort of inference domain of these ecological domains. But what we understand about agricultural production is that it's constrained by many other soil factors, and so these ecological domains are a good baseline to start to understand what the sort of environmental context is, but does not necessarily directly apply to production systems. So a request for information was put out to ARS sites nationwide, and really started in 2011. And as those original sites began to organize and understand really what a development of a national scale network was going to require, requests for information were put out to other sites to cover these general topics here, which was productivity, the infrastructure. This is at the site itself, the infrastructure to do research, the historical data richness and availability of that data, the inference domain of that particular agricultural, that ARS location, varying partnerships that already existed for the sites, as well as how that site can contribute to the overall network. So this information was really brought together, and a group of sites were determined that could contribute the best or the most to the widest domain of inference over the country. So these are the 18 sites. You can you can see they cover a wide geographic range, and when we talk about long-term agricultural research, we're talking about pretty long-term. Some of these sites were established in the early 1900s. Many of them have comparisons of cropping systems that have been going on for 50 to 80 years. And so these sites that you're seeing here are unseen in the world. I mean, there are very few sites that have this type of rigorous scientific comparison at either at the landscape or field scale. And so the network itself has a lot of embedded data and a lot of embedded knowledge just from the very start, because of the way ARS operates, and in terms of having historically maintained long-term research sites. And then you'll see in this my right-hand column, these are a list of networks that these USDA ARS sites already belong to. So you can see that data had been being collected in these standardized formats among many of these sites. And one of our goals was to utilize this historic legacy data to help us understand these sites and how they connect between each other, but then also moving forward, really develop an infrastructure that will allow us to model better into the future. So here's a distribution of the 18 sites across the US. And the network is really focused on a shared approach of testing sustainable intensification strategies at different scales. And we want to seek to quantify the uncertainty. That kind of relates back to the last talk, but also use these specific sites to extrapolate to broader regions, and there's a lot to be gained from that, but also learned from that as well. So this overlaps with the USDA ARS area locations, and so among all of these geographic types of distributions, we have political separations that we deal with as a network as well. So some of the initial analysis that went into this were lots of GIS and geographic information types of analyses, which allowed us to understand the regionalization of the agriculture in different locations. And I'd like to point you out to this publication down here from 2001. There's subsequent publications where the regionalization group goes into much more detailed description of how agriculture is distributed across the country, as well as how it overlays with socio-economic demographics, as well as geographic features. And nationwide, using some of this data, we know that our network accounts for about 50% of all the cereals produced, about 30% of the forages, and 30% of the livestock. And so our goal is to understand the whole country. So we will this is not a static network. We're growing as we speak. So the locations were chosen based on these long-term data sets, identification of stakeholder engagement, looking for interdisciplinary teams that can work at all of these sites. These are all federal employees or associated university and or other agency teams that are at each of these sites. And also we wanted, because we're a research agency, wanted to impose really a treatment design and just understand how, if in a land management decision scenario, you were to choose an aspirational system as opposed to a business as usual system, and really that would be defined by your regional ag production system, how do those compare? And that was one of the criteria we looked for here, because we didn't want this to just be monitoring, but also to be experimental and informative from that standpoint. So, and we understand that different issues would be present in different areas, and that was part of the goal, to really cover the whole U.S. Okay, I'm just want to check my time really quick. I think just about done. So the network objectives, we have a number of working groups that cover everything. It will cover many of the different topic areas, and that also includes common experiments and common measurements that are developed among the working groups. But also we have a focus on communication as well, and outreach. There's a number of groups that focus specifically on partnerships and engagement with stakeholders as well. Okay. And this is just a description of one of the business as usual or aspirational comparisons. And really this is focused in on a different area, but what you can see is that it is multifaceted, and it's not just changing one variable, but using integrated approaches to overcome many challenges that may be facing producers in the future. This is just a list of the working groups that we have currently. There's 2 common experiments that are distributed among the croplands and the rangelands. And the working groups really are distributed sort of all along within these different common experiments. So within the soils working group, and Dave will talk a little bit more about some of the activities there, we have about 40 active members, so that's a big group to manage. There's 120 people. These are 120 listed members on our registry. And so it's a very sometimes unwieldy group. We have 5 national scale projects, a soil data inventory, curation, and harmonization. And if you go to the website at the bottom here, you can see more of that, some tools we've developed. And we've developed some protocols that we're implementing on protocols.io that standardize to some degree soil organic matter sampling as well as soil health assessment. And we've run into some of the same problems that Amanda spoke about previously in understanding what does an indicator mean for a particular land use or place and time. We have a carbon stocks and flows group, and then also we're doing a threat to soil health and sustainability assessment. We coordinate quite a bit with NRCS in some of the standards that are used for the conservation practices, and that seems to be a very good way for us to take some of these protocols that we're developing and harmonize them with NRCS as well. Okay, so takeaways. Communication among your group is key, and this is meetings, shared documents, resource sites. Data curation and stewardship among all these different long-term sites was a big hurdle for us to overcome, and we had to develop specific tools, but we realized that there's a lot of power in that legacy data if we can understand it before it's sort of too late and not interpretable for future generations. Pay attention to the scale and inference domain of your information. We run into that over and over again. I think touching back on the previous talk a little bit about keeping an open mind and looking for new ideas, and if you're designing a research intake system, it has to be able to intake new types of data and be open to new approaches to thinking about things, and then be mindful that a national network or international working group is both scientific and social, and that's sometimes hard for scientists to deal with, the social part, but it's the reality. So that's it. I think I might be over time for us, but thank you. And any questions?
Morning here anyway. I'm Dave Huggins. I'm a soil scientist with the USDA ARS located in Pullman, Washington. And I'm also and in addition to being part of the LTAR national network and part of the leadership team there, I'm also co-director of the Northwest Climate Hub. And part of this presentation is LTR related, but also has contributions from the Northwest Climate Hub. And one of the challenges, and I think Amanda framed it up fairly well, that we're dealing with is from the standpoint of soil health, is trying to establish indicators and relevant kinds of quantitative and qualitative assessments of soil. And I'm going to be talking about some of our efforts in soil health. And I kind of like to bring Wendell Berry into the room. What we do to the land, we do to ourselves. It's very true. And I want to recognize some of my co-authors here, including Jude Maul and Sherry Spiegel, as well as the LTR Soils Working Group and a host of the current 18 sites. And let's see. I'm trying to advance my screen, and of course, it's not going down now. There. Part of our efforts, and the LTR has a national strategic, a new strategic plan, and part of that are 7 different initiatives. One of them being to develop an indicator framework, and you'll notice that there's a multi-factor framework that we're currently working on that's been developed through consensus, and it includes dimensions of social, economic, as well as biophysical or environmental. And you'll notice that within that there's attributes and then indicators, and then the little dots are metrics for those particular indicators. And one of the toes, as I like to refer them to, is soil health. You'll see that up in the upper corner here, soil health as part of one portion of this indicator framework that's trying to look at both trade-offs and synergies that might be expected with the application of different kinds of agricultural systems, with the expectation that there's no perfect agriculture out there, but from a scientific perspective, we'd really like to know what those trade-offs and synergies might be. So in trying to develop this indicator framework, we wanted it to be relevant to diverse stakeholders at multiple scales, both local, regional, national, and international. We wanted to identify and assess LTR site level and network-wide issues, processes, management, and outcomes of interest. We wanted to make sure that the indicator framework represented the uniqueness of individual LTR sites, as well as the LTR network as a whole. And we wanted it to lend itself to modeling and simulation of alternative agri-ecosystem scenarios. Many of you, of course, know the definition for soil health, but I wanted to focus on just the blue part here, the capacity of a soil to function. And often then this is a consequence of a combination and integration of physical, chemical, and biological processes that occur in the soil and the emergent properties of various kinds of functions that soil can contribute to our overall ag systems. Many of you may be also aware that the first status of the world's soil resources was published back in 2015 as a result of the efforts of the Food and Ag Organization of the United Nations. And within that report, they identified 10 major threats to soil health or soil function. And they include, in order of importance, soil erosion, soil organic matter loss, nutrient imbalance, soil acidification, soil contamination. This is could be through agrochemical use or heavy metals, etc. Loss of biological diversity, salinization, waterlogging, compaction, and soil sealing. So we decided to use those threats to soil function and conduct a qualitative survey across the LTR network sites to look at the impacts from a qualitative perspective again of what we call our prevailing or business as usual kind of management that's part of the common experiment of LTAR. versus our alternative or more aspirational kind of management. So within that common experiment, each of our LTAR locations has this comparison. And we wanted to, again, do this qualitative assessment based on basically 5 different qualitative values. One being a major contributor to the threat in terms of that management system. 2, a contributor to the threat. 3, does not impact the threat. 4, buffers soil from the threat. 5, reverses the negative impact of the threat. And also not a threat at the site, being a 5, and also possibly a threat, but unknown, kind of in the middle, 2.5. So we did get responses from 13 LTAR sites to date, and this represents 18 studies. And I wanted to present some of those kinds of results that we've seen to date. Again, I want to mention that this has been a great exercise for each of the sites to go through, particularly with their relevance or not to those 10 major threats identified by the FAO. So what it kind of looked like for the Cook Agronomy Farm, which is located near Pullman, Washington, and collaboration with Washington State University and the University of Idaho and others. And we're using radar plots here, again, going from 1 to 5 in terms of a qualitative assessment for each of these 10 threats. So you can see erosion, soil organic matter, nutrient imbalance, acidification, biodiversity, et cetera. And in that, then you can see the red being kind of the prevalent business as usual site versus our alternative, more aspirational site. I'll mention that our aspirational site of the Cook Agronomy Farm is continuous no-till and the use of precision ag kinds of technologies, whereas our prevalent is reduced tillage and more uniform application of agrochemicals. And so you can see that we're making grounds in terms of erosion and soil organic matter, probably nutrient imbalance too, nutrient imbalance being either more or less nutrients than you may need, and some of the precision ag weighs into this. Acidification, maybe not so great, and we're noticing acidification, at least near the surface, under our no-till conditions. Biodiversity, again, we're not really sure how to go about measuring it. We think we're positively impacting it, but we don't have really good quantitative ways that we've defined in terms of assessing biodiversity. Contamination, we're not so sure about. Salinization really isn't an issue at our site, so that's a 5 in this case for both business as usual and for prevalent and alternative or aspirational. Waterlogging, maybe not impacted by our management in these cases. Compaction, maybe a little bit worse, particularly near the surface under no-till. Surface sealing, better with our organic matter levels near the surface and less crusting. And so this is then a radar plot to assess the qualitative trade-offs that we may get with a particular kind of more systems-related management in terms of one cropping system, in this case, versus another. And this then it was done, and we have done across all these different sites that have responded to date. And you can see some really diverse energies and trade-offs as you go from site to site in terms of these 10 different threats to soil function. And you can also use then this qualitative assessment to basically average from 1 to 5 across the sites to provide kind of an overall network-wide assessment of what we're actually dealing with in terms of soil health throughout the network and where we're hopefully positively impacting different kinds of soil functions. And you can see from a network-wide perspective, we're seemingly addressing some of the erosion, so organic matter, the nutrient imbalances, acidification, maybe not so much, biodiversity, some uncertainty there, and contamination, probably not, at least that we're not aware of. Salinization, again, probably not represented well within our sites. And waterlogging, maybe addressing to a certain degree, compaction to a certain degree, and surface sealing. Note that our alternative or aspirational is usually coming out positively across most of these various soil threats as compared to the kind of the prevalent business as usual. So this again provides kind of an overview our network in terms of how our common experiment, which includes this prevalent versus alternative, is addressing threats to soil function. And you can also divide it up according to the various threats as well to see how they're either relevant or not so relevant amongst the various LTAR sites. And so here, all the sites are around in terms of those that have responded to date around the outside, and you can see the same kind of assessment through a radar plot to look at what we're addressing and what we're not addressing. Again, trade-offs apparent as well as some synergies. So kind of some of the conclusions to date that is that the qualitative assessment was valuable for site level as well as network-wide interpretations. Some of the synergies and trade-offs of management impacts on soil health threats were displayed. We identified some of the largest soil health threats as well as those not previously realized or well quantified. I'll point out that many of the sites noted that soil biodiversity was important, but they really weren't characterizing it in a very quantitative or qualitative perspective or way. And then we identified which soil health threats that were most relevant for an LTAR site, as well as those threats represented by the LTAR network. In other words, the salinization really wasn't a threat that we were representing with our particular site. And many of you, of course, may realize with sea level rises that salinization is becoming more of an issue, particularly along coastal regions. Wanted to dive in a little bit in terms of some current and next steps on particularly referencing the Cook Agronomy Farm in terms of moving forward. And again, trying to identify some of the key metrics to represent each threat to soil function and to further enable some of the quantitative assessments where we'd like to move beyond just a qualitative perspective. And so I'm going to provide some of our experience at the WSU Cook Agronomy Farm, which was established in 1998 to the present. On the left, you can see that we have the business as usual, which is kind of on this left-hand side of where I'm pointing. Hopefully you can see my mouse moving around. And then there's the right-hand side. So this portion is 92 acres, and there's another 60 acres that are over here. So we're looking at more field scale kinds of assessments where we've tried to capture different soils and terrain attributes. And if you can see these little dots in here, those are georeferenced locations over 600 where we've been following various kinds of outcomes in terms of our agricultural systems through time. And I'm going to talk primarily about results from those georeferenced locations. Here you can see soil profiles from those georeferenced locations, quite a bit of variability across this site. We go down to 5 feet or about 1.5 meters, and we look at things from 0 to 10, 10 to 20, 20 to 30, and then by horizon as we go down to 5 feet. And so much of the data I'll be sharing with you is a result of that type of sampling strategy. Again, at georeference points, there's basically a point every 100 feet or so across these two land areas. And you can see some of our other activities in terms of harvesting, et cetera, at these georeference locations. Some of the different soil health properties that we've measured through time. I have a long list here, again, trying to explore what kinds of tests may be relevant from the standpoint of various kinds of soil function. Much of it does come back to trying to define site relevant thresholds and or boundaries of interest. And here you're looking at soil organic matter, and we've established kind of a lower threshold that's relevant to the Cook Agronomy Farm of about 3% or 30 grams per kilogram as a lower threshold that we'd like to target then as if we're above that, we're healthy, quote unquote, and if we're below that, we're starting to be unhealthy. And this then provides more of a conceptual framework of how we're looking at a particular indicator, so organic matter over time, over long periods of time, to see how it see its relationship to a threshold. And then in turn, we also would like to know how various kinds of management scenarios might impact the direction and amount of change of that particular metric, in this case, so organic matter. And you can see here various basically information that derived from research to see what kinds of impact we may have on soil organic matter, including no-till, mixed perennial annual, as well as kind of the wheat fallow or business as usual kind of scenarios. This is what that looks like a little bit at the Cook Agronomy Farm at georeference locations for the top 10 centimeters in this case. And so you can score from a quantitative perspective, you can score each metric relative to a threshold or boundary. And you can also chart that. So in other words, flipping back up here, we could see, oh, if we're located near this threshold, and we could say that we're 100% of that threshold, that relative value then can be used from a quantitative perspective to look at a particular metric across the network without actually having the same measurement, as long the measurement or the same kind of analysis, if you will, in terms of trying to assess, in this case, soil organic matter. And so we're also interested in assessing the spatial and temporal extents that identify where and when that benchmark is met. And here you can see the example where in our long-term no-till, yes, the green is where we're meeting some of our soil organic matter, either above, where we're above that threshold of 3%. And you can also see in the red here where we're below that. And you can see the business as usual is below that 3%. And there's actually portions of our farm that haven't been able to respond even over the course of about almost 20 years of no-till to increase organic matter to what we would consider to be healthy thresholds. But much of the acreage, in this case, in terms of what's shown here, is meeting that particular metric. So this kind of points to the importance of having long-term experiments. Again, the Cook Agronomy Farm established back in 1998. Here are some of the soil organic carbon stocks in the top 10 centimeters, starting off with a history of reduced tillage and then conversion to no-till in 1998. Our no-till was conducted with a one-pass operation using a Great Plains drill, which is a low disturbance a double disc drill, and we saw noted increases in soil organic carbon in the surface 10 centimeters during the course of the first 11 years. We were having compaction problems with this particular drill, so I switched over to a horse drill, which has a much higher disturbance hoe type opener, still a one-pass operation. And you could see an instant, over the course of the next 7 years, you could see that our organic carbon in the top 10 centimeter actually declined. And basically it's very similar to what we started with, because we're basically mixing through this high disturbance no-till, quote unquote, no-till drill of the soil organic matter. We also wanted the capacity to forecast the likely state of soils under specific systems of land management and climate. I see Gabe's up there, so my time must be pretty close to being up. I'm going to go through this quickly for soil pH. Again, soil pH is an indicator. Here's yields, different kinds of thresholds established for different crops, legumes versus wheat. We have issues with aluminum toxicity in this case that are well known. And this is what this looks like for soil pH. You can see the red being bad, basically, and not much in the green from the standpoint of soil pH. Interestingly enough, and no surprise, in the top surface, we're acidifying the soil through the application of synthetic nitrogen fertilizers over time. And very, very red. Interestingly enough, though, that in the subsoil, 90 to 150 centimeters, that 3 to 5 foot level, we're actually improving soil pH from where we started from under our business as usual, which is interesting in and of itself, but also, again, reflects the importance of field scale kinds of measurements and assessments as over time to see how different terrain and soil are interacting with hydrologic processes at the field scale. So thank you. And here's harvesting winter wheat on the Palouse in Washington State. And LTAR is certainly a transdisciplinary challenge for us.
Great. Thank you so much, Dave. And I believe Jude is going to join us for just a couple minutes of question and answer. As a reminder, I don't want to sound like a broken record, but there is that one question survey for audience participants. Please answer that, and please feel free to post questions for our presenters in the chat. I know, Jude, thank you for the work you've been doing to answer some of those questions proactively. But one that came up that we didn't get a chance to answer yet is about particular farming equipment. Dave, I know you're talking about this major change in soil organic matter just by the choice of the drill, but are there equipment purchases that you think would be most effective, or what capital investment should dryland farmers be encouraged to make for the benefits of soil health?
Yeah, I can take a quick stab at that. And of course, again, I want to emphasize that this will be unique to the operation in of itself, what kinds of equipment they already have and what kind of economic state that they're in. Certainly, investment in equipment that moves towards less soil disturbance is usually more positive from the perspective of many kinds of soil health metrics that we've seen over time. And so I would encourage the use of various kinds of one-pass operations that at least lower disturbance. Much of this is reflective of our efforts along soil conservation and recognizing that soil erosion is a chief a soil degradative process for us, and it's probably number one given our soils and our topography that we have that we're contending with. So I would say that's some of the considerations. Of course, it gets more complicated than that, and often we're looking at different kinds of implements to address various kinds of soil health issues like compaction, et cetera. So everything from vertical kinds of tillage that try to disrupt some of the tillage pans that we may have that may be impacting us, and other kinds of implements. There's a lot here to unpack from that perspective. And happy to talk about it more, but it could probably take the rest of this time.
Fair. Well, thank you. Thank you for that answer.
And I would just say, from in Maryland, where erosion is not as much of an issue, that lack of disturbance is still as critical because it turns into compaction. And because of the different soil types, the very clay soil types, we develop clay pans, and it can really interfere with a lot of other growing operations.
Great perspective. Nice to have that regional or that national LTAR network so you can make those kinds of comparisons. Speaking of the network, that's one slide of the radar plots across the whole network clearly showed that you have, that you have improvements with these aspirational or alternative treatments relative to kind of conventional or most prevalent treatments. And I wonder how does that get translated to practice from the network, and how does the network go about documenting impact?
Great. I don't know if you want to take a stab at that, Jude, but I will tell you, of course, that one little soil health toe, as I call it, is just one part of that indicator framework that really is trying to assess things from a social and an economic as well as an environmental perspective. So what we're grappling with now, of course, is to try to discuss and come up with methodologies that cover that whole framework that will enable us really, hopefully, to qualitatively and quantitatively try to assess some of these trade-offs and synergies. I think this is a huge challenge, of course, and I'm smiling because I'm not sure how exactly we'll achieve some of this, but steps forward are looking at examples like I put forth here. Even the example I've given isn't one that's set in stone. It's under consideration, and it will no doubt evolve over time in terms of what it looks like. But I thought it at least provides a way to basically respect the uniqueness of each site while still lending itself to more of a network-wide analysis. And I'm hoping that we can I'll be pushing, and others for trying to develop this throughout that indicator framework.
Great. Well, thank you both so much for talking with us and for letting us learn from the LTAR network. Unfortunately, we're out of time, but if you want to take a look at some of the additional questions in the Q&A, feel free to answer those offline.